The name of the video is Current Intensity. Consider two conductors in vacuum, A and B. These two conductors are in vacuum and are fixed in an inertial reference frame inertial I reference R frame F. In addition, they are in macroscopic electrostatic equilibrium. Macroscopic M, electrostatic E, equilibrium E, MEE. Let us assume that at time t equals 0, the charge on object A is a constant, which we just call QA. Whereas at the same time, the charge on object B is equal to 0. Let us assume that these two objects, these two conductors, reside within a superregion capital sigma. We know that for such an isolated system, the charge conservation principle has to be true, has to be valid. What is the charge conservation principle for this isolated system? The charge conservation principle tells us that the charge Q at any time t contained within the superregion enclosed by the surface capital sigma has to be equal to a constant. If this wasn't true, the charge conservation principle, which is a principle, so it's an empirical law, it would be not fulfilled. Under these conditions, suppose to perturb the macroscopic electrostatic equilibrium condition of these two conductors. How can we do that? For example, we can do that by means of a very tiny wire connecting these two objects A and B, these two conductors A and B. The wire is so small that there is no charge accumulated with it, so I assume that the charge on it is 0. So it only serves as a connection, as a channel to move charges from A to B. So for example, this object could be realized in experiment. Of course, you can use a copper wire, or if you want, in the typical experiments people were doing in the beginning, when we were trying to understand this scenario, they were using a wet wool thread. So why did they want to use a wet wool thread? Because by means of soaking in water, this thread it contains ions that therefore charges, which are free to move over the thread. And so when you do that, with a conductor like a copper, the movement of the electrons on the copper, we will come back to the concept of electrons in generating a current soon, in a future video. But if you use a conductor like copper, this phenomenon is super fast. And so with the technology available a couple of hundred years ago, when people were trying to understand the scenario, they prefer to use a wet wool, because in this case, the ions move much slower over this connection, this channel between A and B. And so if you have a stopwatch and a meter, a charge meter, you can actually perform a reasonable experiment within reasonable time scales. Nowadays, of course, we could do something a little bit more advanced, like with a copper wire. But this is historically what happened the first time people tried to understand this kind of experiment, this kind of scenario. All right, so now that we know that, let's already write down here the two key ingredients we will need to perform this experiment. So we have a wet wool, and then we need a stopwatch and we need a charge meter. These are very good ingredients to make an excellent experiment. Okay, so now we have the settings of the experiment here. And suppose now, as soon as I connect these two objects by means of this wire, charge begins to move from A to B because I perturb this macroscopic electrostatic equilibrium. And so the experiment tells us that if we were able to measure at each instant of time the charge Q on A at time t, this charge on object A, as soon as I connect it to B, which was discharged, decreases, whereas the charge on B increases. It's like in thermodynamics, when you have a hot object and a cold object and you put them in the same room, they tend to equilibrate. So here is the same kind of principle. There is a sort of equilibration phenomenon going on. So the charge on A decreases, whereas the charge on B increases. And so if I sum them up, though, since this is an isolated system, no matter what do you think will happen to the sum of these charges? Of course, because the charge conservation principle, it has to be equal to a constant. What constant? The overall charge at the beginning of the experiment, which was Ka at t equals 0 equal Ka, Qa. So Qa at t equals 0 is Qa is a constant. When I do not specify explicitly the time dependence, it's just a constant. So Qa at generic time t plus Qb at generic time t is equal to a constant Qa. Qa decreases at time t, Qb increases. And this remains constant. Charge conservation principle. Great. So now we have this great law here in front of our eyes. It is worth performing a time derivative. So we get rid of this constant. Very typical procedure to get rid of constants in physics. And so when we do so, this becomes 0 on the right hand side, the derivative of Qa, which is a constant. So we can rewrite this as minus the derivative of Qa, function of t, with respect to t, is going to be equal to plus the derivative of Qb at time t divided by dt. Note that it's quite important to stress this fact, this minus sign here. Qa decreases, so charge exits from object A, from the conductor A. And this is encoded mathematically in this minus sign. So whenever something decreases or exits an object, we have a minus sign. This is actually very important in understanding the continuity equation. So if you don't grasp this minus sign and its concept here, it's going to be very hard to understand the continuity equation in a couple of videos from now. Okay? So this is very important. So here, of course, the charge enters, positive sign, here it enters. I'm not going to write it down, but it's the same concept, decrease and increase. Exits, enter. Exit actually is the one I really want to stress here, the minus sign. Suppose now that with our stopwatch and charge meter, we were able to observe what happens at the cross-section capital sigma prime within this wire, where again I assume there is no charge accumulation because it's a tiny wire. So if I do that at any time t and I have a charge meter, what I would measure in this case, it would be something like this. So the charge Q at time t is equal to charge conservation principle, the constant charge Qa, which is the initial charge on the conductor A, minus the variation with time of the charge on the conductor A. So this is general law in this case. Now, in this specific case, if I were to compute, in this case, the time derivative of Qt with respect to t, so of this quantity here, this quantity, the time derivative of Qt measured this cross-section sigma prime, with respect to time, is what we call I, function of t. This quantity I, function of t, is what we call the electric current intensity. Note that this quantity is a scalar. current intensity is always a scalar quantity, not a vector. We will encounter a vector representing current in a couple of videos from now. That's called density, current density. The intensity, it's a scalar, and it's defined in this fashion here. This also tells us that the unit of current the SI units for I are nothing but Coulomb divided by second, and this quantity, we call it capital A, or if you want, ampere. In this discussion, we forgot two main concepts. First of all, the direction of reference for the current. And second, the charge, the sign of the charge is moving across this wire between A and B. So let's make a simple table with 4 entries. So in this table, we're going to have all these possible scenarios. So we can have, for example, we can assume that the carriers across this wire are positive charges, or they could be negative charges. In fact, if you're using a wet wall, there will be ions which can be both positive and negative. Note that if we were using a copper wire, let me ask you this on Piazza. If I were to use a copper wire instead, if this one is just a copper, in this case, what kind of charges are you going to have? Positive or negative? This is the question I leave for you in Piazza. But in general, if I consider a wet wall, of course I have positive and negative. And in addition, I can choose the reference direction of this green wire, either to go from A to B, or from B to A. So now, from experiments, and also from the definitions given in this board here, clearly, what happens is that when my reference direction goes from the conductor A to conductor B, and I'm using positive charges, I'm considering the motion of positive charges across, let's say, capital sigma prime, then in that case, the current, I, is positive. If I consider in the same scenario from A to B negative carriers, the current is obviously negative. If I invert the definition of reference, I go from B to A, obviously, for positive carriers, the current is negative, whereas C is positive for negative carriers. So they just invert each other. This is actually a very important concept experimentally. So from experiments, what we were able to find out is that the motion, that is the current associated with a positive particle from A to B is equivalent to the motion of a negative particle from B to A. This is very important because, for example, as a convention in circuit theory, if I assume now a copper conductor, where Amanzer is somehow your question here for Piazza, but I think it's actually I will leave it to you also for this in Piazza, otherwise I'm answering this question here. So why do you think this is important in circuit theory? Because in circuit theory, we actually, by definition, we assume that the carriers are always positive. So in circuit theory, by definition, so it's a convention if you want, we assume that the carriers are positive. So I ask you to discuss this concept here, how this is relevant to this kind of definition, and why we can always do that in this definition here, in this model, in Piazza. Okay, so in this video, we introduced for the first time a scalar quantity called the electric current intensity. We have done so starting from two conductors in vacuum in macroscopic electrostatic equilibrium. As we have done for conductors, we want to break that macroscopic electrostatic equilibrium. And how do we do that? We connect them with a wire with very small cross-section, small no charge in it. This breaks this equilibrium, so there is a sort of re-equilibration phenomenon happen like in thermodynamics. So charge starts to flow from A to B giving rise to a current. We can use the charge conservation principle to understand the signs of how this current changes with respect to time, the rate of change, which is the current intensity. Minus means to exit an object A in this case, very important later on in future videos. We set up a nice experiment with stopwatch and a charge meter, and we made a table which takes into account for the various reference directions as well as the possible values of the charge, the sign of the charges. We also define the unit here. That's it.